Hello everyone. Today in this video we'll be discussing what is scalability in distributed systems, what is replication, what is database sharding and database partitioning and what are their advantages. So let's start with the first topic, which is scalability. So in very simple terms, if your system can handle the increase in traffic with minimal to no changes in your system, in your backend application, then your backend application is considered scalable. So let's understand this by an example. So let's say you have a very beautiful backend application which is running in production. So you created a project as a side hobby and then you deployed in the production. So initially it had very limited number of customers or the users. So you had very limited number of requests coming to your backend application. Now your system became popular. Now you were getting more and more requests. So when you got more requests, since this system has limited resources, right? This system has limited resources in terms of CPU, in terms of IO, network, disk, RAM, memory, anything, right? So all of these resources are limited. And because of these limitations, your system was not able to handle the number of requests that is it was getting. So in this case, this system, this application is not scalable because you have to make the changes in the system and to scale for the number of requests that you are getting. So that's why this system is not scalable. So now let's understand why is it important to build these scalable systems and why everyone asks to build scalable systems. So since in software engineering, not all the decisions are reversible and some of them might require a lot of time and effort, and it's your responsibility when you are building the backend application. You think about the growth of the application and how would it evolve in 3 to 5 years. And as a side note, scalability is a non-functional requirement or the expectation from the distributed systems. And that's why it's the responsibility of the engineer who's working on the backend application to build the highly scalable system. So whenever we are trying to build any scalable system, we first start with the very minimal design or very minimal components, and then we try to analyze the single point of failures in the system, and then or basically the bottlenecks in the system, and then we try to remove these bottlenecks from the system so that makes our system scalable. So let's take the example that we have. So initially, like we discussed, we had very less number of requests coming to our system, so we were easily able to handle these many requests. Now as our system became popular and we got more and more requests, because of the limited number of resources, we were not able to handle these many requests. So what could be the easiest solution in this case? How can we handle these many requests? One simple solution would be to throw in more hardware. So let's say initially this backend application was running on certain resources, let's say 5 GB RAM and let's say 1 TB disk and so on, all of these resources, right? Now when we say let's throw more hardware, let's say we increase the RAM, we increase the bandwidth, we increase the disk, we increase CPU, we increased all of these things, right? So that we can accommodate or we can handle the increased number of requests. So the problem is solved. But after 6 months, our system again became more popular and people are using more and more to access our application. Now we'll face the same problem again. Let's say you again did the same thing. You throw in more hardware and you try to solve the same problem by throwing hardware again and again. But there is a limit. There is a hard limit and you will hit it very quickly when your system becomes popular, because you cannot have infinite RAM, infinite memory, infinite disk and so on. All of these things have a capacity, have a limitation. So at some point in time, you'll have to think about redesigning your application so that you don't have to add hardware again and again as your system becomes popular. So this approach is called vertical scaling, where we throw more and more hardware whenever we get more and more requests in the system. But this vertical scaling has certain limitations. The first one is you cannot always keep on adding more and more hardware because you have the limitations of the resources, be it CPU, memory, disk, network, bandwidth, anything. Second major problem with vertical scaling is now that you are adding the resources into your same application, and it's the only application which is accepting the request and processing the request and finally returning the response to your clients, right? Now you see the problem right here. If this application dies, your whole backend is not available. So again, when your system is, let's say, experiencing some kind of failures, your whole application is down. So again, this impacts the reliability of your system and also the availability. So what was the problem that we faced? If your system, if your application is not available, your entire feature, your entire app is not available, because client cannot contact to other application because you only had one instance, right? So these are the problems with the vertical scaling. So instead of scaling your application vertically, in this case you can scale your application horizontally by adding more and more instances to your application and then adding them behind a load balancer. So let's see this by an example. How would your application look like if you add more instances to your application and add them behind a load balancer? So how would the request flow in your system? Clients make a request to the load balancer, and then load balancer will decide which instance I need to route this request to. So the load balancer will send the request to one of your instances, and then that instance will handle the request and finally send the response to your clients. So in this scenario, in this situation, how we handled the increased traffic in the system? By adding more and more instances to your backend application and adding them behind a load balancer. Now all the requests will not directly come to your backend application. They will be routed by the load balancer, and load balancer will decide based on certain algorithm which application instance I should route the request to. So this is how after the horizontal scaling our system would look like. Horizontal scaling. So when we are scaling our application, we have to identify the bottlenecks in the request flow. Like in our case, request was flowing from the client to our backend application, and from our backend application to, and then backend application was requesting some data from the database. So the request flow was involving these components, the backend application and your database. So initially what we did, we identified the bottlenecks in the system. In our case, the bottleneck was application server and our database. So if one of the instance of this backend application goes down, we can simply add more and more instances and we can easily scale our application horizontally. But if you see the problem, our database is still a single point of failure. Why? Because if this system goes down, I mean, if this, let's say there is a power cut or there is any hard failure in the database, and for some reason the database is not able to provide the connections to your backend application, in that case the backend will not be able to fetch any data, and these requests that you were getting right from the client, these need certain data. Let's say you had one user service, maybe this was a user service, right? And it was returning some profile information. So basically when you get the request from the client to your backend application, it fetches the user profile from the database. Now the database itself is not available, so you won't be able to serve this request, right? So all of these requests will keep on failing. Why? Because you left certain bottlenecks in your system. This is fine, this is a green flag, because you scaled all of your backend applications. I mean, you scaled your backend application by adding more and more hosts, right? So this is okay, but your database is still a single point of failure. So we need to again remove the bottleneck and we need to scale our database as well. But remember, database scaling is different from the application server scaling, and database scaling is achieved through the combination of different techniques. So before we actually scale our database, let's first understand a few concepts. How can we actually, what techniques are used to scale your database? So the first thing is replication. Like the name suggests, we replicate the data or the operations from the master node to the slave nodes. And in SQL databases, we can run our databases into master configuration, where you have one master node and other one is just a follower node. I mean, so all the writes from this application will go to this master, and once the writes have happened on this application or on this database, it will send the copy of the operation to its follower node. Now it's the responsibility of this follower node to apply the same operation on its data. So at any point in time, whatever changes have happened on this database will also have these changes. Now if at any point in time, assume that this database is not available or goes down for some reason, then this can become your master database. So basically it's a failover scenario. When one database or one instance goes down, the other one takes over and starts taking the writes. So in this case, at least we removed the single point of failures. So if this database goes down, the follower database can become the master, and then it can start taking the write request or the read request. But there is a problem. If both of them are in a single data center, let's say this is one data center, let's call it DC1. So what happens is, let's say there is a power cut or there is a power failure in the whole data center. So both the applications, both the database instances will not be able to serve the request, right? So we again land on the same page. We again land on the same situation where the whole application is down because our databases are not able to serve the request. So what can we do in this case? So let's try to split this case into another case where our first master database is in one data center and the follower database is in another data center. So let's call it, this is your DC1 and this is in DC2. So if there is a power cut or power failure in one data center, it will not impact the second database instance, and this can now become the master, and then it can start taking the request from your application server. But you see, there is a partition, right? There is this partition because all of these operations that are happening on one database have to be replicated from this database to the follower database, right? So in this case, there might be some latency because the operation or the actual data is being sent over the network, and we know that we cannot trust this network, right? Because of the network failures and all. So keep in mind that all of the operations that are happening on this instance, right, are replicated over the network to the follower database instance, right? And because of the network partition, there might be cases where these operations were not replicated to the follower database, right? So there can be situations where this database might have different copy of data and this database might have different copy of data. So this was a master configuration. Master configuration, where one master node was taking all the operations from the application, and if this instance goes down, right, then this follower second master application can take over, right? And then this will become the master, and then it will take all the operations from the application. And once this node again comes online, this can basically start fetching the operations which are not replicated on this node but have happened on this node, right? So this is a master configuration. Another configuration is master slave configuration, where let's say you have your database, this is your master node, right? And you have multiple read replicas or slave replicas. So what happens is your application will always write the data on the master nodes, right? And once the operation has been applied on the master node and the data has been persisted into the disk, then these operations are replicated to your read replicas. Let's call it R1, R2 and R3. So whenever the application wants to read some data, it can read from the master database or it can read from the read replicas as well. So in this case, what we did is basically we tried to split our write traffic and read traffic based on the configuration that we were running, right? Why? Because read replicas might not have the exact data because of the network partitions, right? And we also discussed it's not a good idea to keep the whole configuration into one data center. So this is, let's keep it in one data center, right? So again, if there is a power failure in the data center, we might not be able to serve the application request, right? So it's always better to keep your read replicas into different data centers. At least keep your read replicas into different data centers. So let's see how would our application look like once we apply these changes. So this is the final architecture of the system, right? So let's understand the request flow. So let's say user wants to fetch the user profile, right? So it lands onto the load balancer. Now the load balancer will decide which instance should handle this particular request, right? Let's say it's a read request. So we will go to one of our read replicas and fetch the data from there and then return the response back to our client. Why? Because we split our read and write traffic, right? So all of the writes will go through our leader node and all the reads we will serve from the read replicas. Now let's say if we get a write request. Let's say if we get a write request, how would our system look like in that scenario? So you got the write request from client, right? And the load balancer will decide which backend instance should handle this particular request, right? Let's say it picks the first one, and then this backend will write to the master node, right? And once the data has been persisted, right? Let's say the data has been persisted, so it returns the ACK to its backend application, and also it will replicate this operation to its read replicas as well. And it depends what kind of algorithm we are using to make sure that this operation has been persisted in this configuration or not. So then this leader will respond to the application with ACK, and then this application will respond to its client with the ACK that the changes have been persisted. So this is how our whole system would look like once we make sure that we remove all the bottlenecks or all the single point of failures from the system. So now let's understand what is the impact when we scaled our databases, DBs, and our application servers, right? So what happens is now you have multiple applications and single leader right now. And let's say after some time, let's say down the year, your system again became more and more popular and more people are using your application or your backend application, right, to access the features. Now your backend is writing more and more data to the leader, right? So what happens is over the period of time, the data in the leader node will become huge, right? Obviously, when you get more and more requests, you will be writing more and more data to your backend application, your databases. So let's say this is your database master. Now let's say this database has 1 billion records, and now again you're facing the same problem. Now your database queries, read or writes, have become very expensive. Why? I mean, let's say you still have the indexes on certain fields on which you are querying, right? But as we know, whenever you create an index, you also create an extra overhead in the system, right? So first the database will have to update the row, insert the row into the database, and then it also has to update the index as well, which is being maintained, right? And if you are reading from the index, so it has to keep the whole index into the memory, and into the memory I mean into the RAM. And over the period of time, if you keep the whole index into the memory, that's an expensive operation for sure. So what we can do in this case, and that's the situation where the database partitioning comes in. Partition, right? So what happened is, you try to split your whole database, I mean whole table, right? You split this table or slice this table horizontally. Now this piece of data will stay on partition 1, which is P1. The second will stay on P2, and so on. So now what you did is, you try to split this whole table into subtables. And now your database will try to manage these subtables or these partitions as an independent table. So initially you were searching in the whole 1 billion records, right? Now you will be searching in this partition, but you have to provide the partition key whenever you are searching for any record, right? Partition key. So right now we are not discussing in too much details, but I just wanted to say what is database partitions and why do we need the database partitions in the first place. So when your tables become very huge, right, and your any operation on the database table becomes very expensive, then you have, and again this data, right, I mean this is a single point of failure again, right? If you're writing on one data source and if it goes down, then you won't be able to perform the writes in the system. So the first technique is called the database partitioning, where we try to split the big tables into smaller tables, and now database can manage these smaller tables into independent database table. Now the advantage, what's the advantage that we're getting? So if you have certain indexes, right, let's say on first name, ID, these indexes could be on any field, right? So these indexes are limited to the partition, right? Because the database is managing these partitions as a separate table or as an independent table. So whatever the data is present on that partition, your index will have that many records, or it will manage only these many records in the index. So even if you are bringing the whole index into the memory, right, it's still not that expensive, right? So now what's the query pattern? So first you need to provide the partition key whenever you're searching for any attribute, any record, right? And then once you provide the partition key, then the database will go ahead and try to fetch the data from that partition, let's say P1. So you added one extra layer, right? And if you do not provide the partition key while fetching the data, right, then it has to query the data. It has to query the data from all the partitions that are available in the system or for this particular table. So let's say there were 1, 2, 3, 4, 5 partitions in the system, and if you do not provide the partition key, then the database will query the first partition, second partition, third partition, and all the partition until it finds that particular record that it is looking for. So again, you see the problem in this situation, right? Now the latency of this read request becomes very expensive if you do not provide the partition key. And another problem is, since you did not provide the partition key, right, the slowest partition will decide what will be the response time or the latency from the database, because it cannot return the partial results to its client, right? In our case, it is our application. So it has to first wait for all the partitions to result the data, return the data, and then it can return the data to its application. So that's another disadvantage of having the partitions. Another topic is database sharding. So database sharding is like the partitioning, but when we create the partitions of particular table, right, these partitions will not live on a single instance, they will go to different instances. So this was your, let's say, big table, right, and table, and this is your partition p1, this is your partition p2, p3, and so on, right? So all of these partitions were on a single machine when we do the database partitioning. Single machine. But when we want to shard the data, we first pick an attribute, which attribute we want to use to shard the data. Let's say in our case it could be, let's say, id. So we had, let's say, a table which has id, name, email, etc. So we can use id, and this id field is, let's say, auto increment. So we say, let's say, 1 to maybe 100,000 on a first shard. So that means first partition live on the first shard, and 1001 to, let's say, 300 will live on the second shard, and so on. So in our previous scenario, what was happening, all of these partitions were on a single machine, on a single physical machine. Now these partitions are spread across the different machines. Now you see the problem again. So let's say this is your first partition, this is your second partition, and this is your third partition. So p3, p2, p1, and remember, this is on shard 1, this is on shard 2, and shard 3. Now the application, how would the application know which shard to query the data from, right? Because it does not know how to fetch the data. Let's say it's looking for id equal to 3. So I want to fetch the record or the row where the id is equals to 3. How would it know that this id is present on which partition or on which shard, right? So this application, that this logic of deciding will have to be part of the application itself. Now before your application queries the data, your application has to know, if it is querying for id equal to 3, then it knows it has to be on partition 1. And if it's, let's say, fetching the data, fetching the record when id is equals to 001, then it knows the data will be on partition 2. So there is a problem right here. And what's the problem? The hard coupling. Now your database is hardly coupled. I mean, your application has to know the state of the database, what all records are going where, so that it can query the data from that shard. So that's one disadvantage, but yeah. So now let's discuss what are the advantages that we're getting when we do the database sharding. So the first one is, we can always scale horizontally our databases. And what do I mean by that? Is we can simply pick a particular attribute, split the data, and then distribute it across the different shards. Now that shard becomes responsible to handle the operations on that particular data, or providing the data for that particular, from that particular shard. So horizontal scaling is good. Second thing is, now your read request or the write request will become faster, obviously, because you're working with less data, right? And the a particular shard will have certain or the limited set of data. So all of these indexes or all of these things will be limited, right? Because all of these things will be built on the data which is residing on that shard. So your queries will become faster. But what are the disadvantages that we are getting when we do the database sharding? First thing is, now your application is tightly coupled with the database. Why? Because if you see here, right, this application has to know beforehand which shard holds which particular data. Otherwise, it will have to query all the database shards, right? So you created a hard coupling or tight coupling in your system, which is a big problem. And the second problem is, when you split the data and spread it across the different shards or the different nodes, you cannot perform the joins. And the third and the very important property is, when we do the database sharding, we cannot guarantee the ACID properties. We will discuss these ACID properties in the later videos, but for now, when we do the database sharding, we lose the access, or we cannot guarantee the ACID properties when the database, the table is spread across the different shards. And the fourth problem is, when we do the database sharding and let's say a certain piece of data or certain set of data is being accessed more, right? And if, let's understand this by an example. So let's say we have, let's say id equal to 5, right? And this is on first shard S1, this is your S2, and this is your S3. And let's say this is your application. Understand this data where the id is equals to 5, or let's say a set of ids, let's say 1000. Let's say these ids are being accessed more compared to other. That means, and let's say this data is on S1. So your application will query this data too much, right? That means this shard becomes hot shard. Why? Because a certain set of data is being accessed more compared to others. And the next problem is, since this shard is responsible, right, to provide the data that it owns, and if this shard dies, you lose the data, right? Because you don't have the copy of this data anywhere else. So you have to replicate the data on this shard, which is available on this shard, to other nodes as well, to make sure that you do not lose the access to the data. And the last one is, let's say your table is becoming huge again on a particular shard, right? Then you have to reshard that shard. Let's say your S1 was holding more and more data, right? So you again shard it by the same ID, right? Or maybe different ID as well, but let's not complicate it for now. So see, every time when the logic on the database changes, you have to make the changes in your application as well, because the application has to know which shard holds which data, right? So that's another disadvantage of the sharding. So back to our main topic. Let's see how would our system look like when we made all of these changes, all of these concepts to scale our system, right? And let's see how would our final system architecture would look like. So it would look something like this. So let's see the data flow in the system. So when the clients make a request to fetch certain things, let's say it's a read request, right? So client makes a request to load balancer. Load balancer will pick one of the instance. Now this instance will have to fetch the data from somewhere, right? From the data source. Now first this piece of logic, and this logic is responsible to provide the information related to the shards, like which shard might hold the data for this particular ID. And this logic that we have might also evolve into its standalone service, or could be, let's say it could be one thin service which will handle all of these requests and provide the information about the shard. But then again comes a lot of problems. So for simplicity, I kept all of this into a single piece of logic. So this piece of logic is just to get which shard might hold the data for this particular ID, right? Since it's a read request, let's say this is a ID one that user is trying to fetch. So this will not user, the client, right? The client is trying to fetch the data for ID equal to 1, right? Now we kept the behavior for this architecture like the architecture we had before, where we split the read request and the write request, and all the writes go through the leader node or the master node, and all the reads will go through the read replicas. So when we are reading, we fetch the data from the read replicas and return the response back to our clients. And let's say when the user is trying to write some data, let's say they want to change their profile name or something like this, right? So the request again goes to your load balancer picks a particular instance, and then this instance will decide, okay, because of this logic we will be able to figure out, okay, which shard is responsible for this piece of data, right? So we go ahead on that shard and do the write, and when we get the ACK, we return the response, and then this application will return the response to your client. And then once this change has been persisted on the write, this operation will also be replicated to your read replicas, so that they can also maintain the same state what you have on your master node. I guess that's it. This is how your final system architecture would look like when you want to scale your system and try to remove the bottlenecks. So what we discussed in this video so far: first we discussed what is scalability and why scalability is important. Then we discussed application server level scaling. How do you scale your application servers? Third, before we actually discussed the database scaling, we first discussed certain concepts, and the first one was replication. How do you replicate the data? Second one was database partitioning, and why we did the database partitioning. When your tables become huge, then all of your database operations become expensive. So we try to split the whole table into smaller partitions, and all of these partitions will reside on a single instance. Then we also looked at what is database sharding. So database sharding was nothing but you create the partitions and then you spread this data across the different nodes. Now that node is responsible to perform the operation, read, write, update any operation on that data. After doing the database sharding, what we did, we tried to split our read traffic and the write traffic. And by having enough replication in our system, we can we can handle as many reads as we want. And how did we scale our writes? We try to split our whole data into smaller databases, and which we call shard or partitions, and we then spread these partitions across different shards. I guess that's for this video. If you like the content, consider subscribing to my YouTube channel, because I'll be uploading more and more videos to this playlist. And yeah, see you in the next one.